today, and specifically we're going to be looking at covalent bonding. We do need to cover ionic bonding and metallic bonding, but we'll do that in the following 2 lessons. So after this lesson we will go on to ionic bonding, and then we'll do metallic bonding the lesson after that. So what we've got here is our electron arrangements for the main group elements, and really when we're talking about bonding, a lot of the time we're going to be talking about these. Now what you'll notice is we have completely avoided the transition metals. So the transition metals are gone from this particular periodic table, and there's actually a really good reason for that. And the reason is valency. So when we're speaking about valency, what we mean is how many bonds any element can actually make. So for example, oxygen is in group 6. It's got 6 outer electrons and it can make 2 bonds. So its valency is 2. The valency of group 1 is 1, group 2 is 2, group 3 is 3, group 4 is 4. Then it starts to go down, so group 5 is 3, group 6 is 2, group 7 is 1, and group 0, or sometimes called group 8 as well. So group 0/8. That last group does not make any bonds at all. Now, what I'll do is I will write above each group the valency for each of these different groups. Now, a group goes down the way, a period goes across the way. Really, periods aren't that useful all in all. It's mainly the groups that we will focus on. So once we get to group 5, the valency goes down to 3, group 6 is 2, group 7 is 1, and group 0 is a valency of 0. Now, what we're going to take a look at is selecting a few of these. To begin with, because we're going to look at covalent bonding, we are only going to focus on non-metals. So hydrogen is weird. It counts as a non-metal, and it also sometimes acts like a metal. Hydrogen's very, very weird. It counts as one of our non-metals. Then, as you'll see on this little bit here, the elements on this side are metals, the elements on this side of the dark line are non-metals. So this is our staircase through the periodic table, and it shows us what is a metal and a non-metal. Metals and non-metals have quite distinct properties. Metals are usually shiny and silvery. They will conduct. They will essentially bond infinitely with one another, whereas the non-metals will not conduct electricity, and they will bond usually in discrete molecules. There are exceptions to that rule, and we will talk about them a little bit later. So this is our little staircase. All of these ones here, all of this bit here, this is I'll try and, oh dear, I'll just underline this, non-metals. So this is all our non-metals here. Non-metal. And these are all our metals over here. So these are our metals over here. I could even change that to a nice silver so that we can see that those are our metals. So if we've got hydrogen, the valency of that hydrogen is 1, and if we've got a fluorine, the valency of that fluorine will be 1 as well. The valencies of these ones are slightly different. So what we're going to do first of all is we're going to recap this outer electron arrangement, and I'm going to show you that on a little bit of paper, and then we'll move on to what happens when we bond these together. Right, let's move on. Okay, so in chemistry, valence is actually probably one of our most important ideas. And this is really the concept that we can go from individual atoms to molecules. Now, if we take our simplest element, we've got hydrogen, and it has a valency of 1. So the first thing that I want to do, and if we are going for notes again, this can be the foundation of your notes. Valency is simply going to be defined here as the number of bonds an atom can make. Now, if we go for hydrogen, the nuclide notation for hydrogen is it has a mass number of 1 and an atomic number of 1. And it's got no charge, so if it's got 1 proton, it must have 1 electron. So if we draw this out very quickly here, our atom's going to look something like this. Now, if we've got another hydrogen atom over here, little positive charge and an electron. So the energy of these two separate atoms, it has a high energy. Now, the universe, for whatever reason, likes to make sure that everything is in the lowest energy possible. Now, that lowest energy possible happens when we get a full outer shell. So, in terms of having a full outer shell, there's really a couple of options we can have. If you're hydrogen, lithium, or beryllium, really your full outer shell can be 2. That's you having a full outer shell. So a full outer shell can be 2, or it can be 8, or it can be another 8, and that's as far as we go. So these are our full outer shells, and that's as far as we go at National 5. And in essence, what's going to happen is atoms are going to bond together so that they think they have a full outer shell. So if we take that concept that we've got these 2 atoms of hydrogen here, and it's quite high energy, these are going to bond together. Now, hydrogen is going to be considered a non-metal, and you'll usually consider hydrogen a non-metal unless you're doing some really crazy chemistry later on in your life. So hydrogen's a non-metal, and it's going to bond to share these electrons here. That share of electrons is a covalent bond. So what we'll have is this is the sharing of electrons between non-metals to produce a full outer shell of electrons. So we've got this covalent bond that's going to form, and that's going to be the sharing of the electrons to have 2 outer electrons. And to show this, we can really draw a Lewis diagram. In a Lewis diagram, we don't show the inner electron, so I will show you this again with a slightly more complex example later on. So what we've got is we've got a hydrogen nucleus, and another hydrogen nucleus. The electron here I'm going to show as being a circle, and this electron here I'm going to show as being an X. And then, to show that these are being shared, I'm simply going to draw as best I can a circle around the hydrogen and the electrons. That places our electrons in the centre. Now, as these two separate atoms were in a high energy state, this bonded H2 molecule will be in a low energy state. Now, that energy's got to go somewhere. That energy has left as heat, really the vibratory motion of atoms, or as electromagnetic radiation, and we usually say heat or light. So that energy has been lost as heat or light, and that makes the universe happier in some way, because the energy is more evenly distributed between all the participating parts. So now we have an H2 molecule bonded by a covalent bond, and there's a share of those electrons there. It is important to note that this is actually just a game. This is just a game to show you what molecules are going to look like, and this game works really, really well most of the time. When you go on to higher and advanced higher chemistry, you will find out that this is not a really very good representation of what's actually happening in this molecule, and you'll go on to study some quite interesting things. But what I want to do is show you this with a molymod. So our molymods, which hopefully once we're all back in school, we can actually have a little go at doing some of this. So really, this is my two hydrogens here. Not very clear to see on white paper. I've got the two hydrogens here, and I'm going to form a simple covalent bond between the two, and that's us got our molecule of hydrogen, and that is our hydrogen molecule just there. And the share of electrons is shown by the little plastic connector, and these are the two hydrogens here. So that is our first covalent bond that we've built. What I want to do is show you a slightly more complicated example, and we'll talk about that, and then we'll make a molecule out of two different elements. So, slightly more complicated version of this might be fluorine. So fluorine has the symbol F, and its electron arrangement is 2, 7. So what I want to do is bond two fluorine atoms together and see how that looks. So I'm going to start with an F over here and a little F over here. Now, the inner electrons do not take part in the bonding, so I'm not going to show those inner electrons in my Lewis diagram. So this would be a Lewis diagram, and I'm not going to show these inner electrons. What I am going to do is I'm going to go round and add in my electrons. Now, I'm going to do this in a way that is a little bit cheeky, but it works quite well, because the way that I would tell you to do it is start at 12 o'clock and go round and continue to fill them up. However, as you'll see, this is going to leave our molecule looking a little weird if we did it that way, so I'm going to show you how to do that first of all. For this fluorine, I'm going to use crosses. For this fluorine, I'm going to use circles. That's just to show what electrons are from what nucleus, although this is not, it's not even really possible to tell that in a molecule. It's good practice at this stage to do that. So we've got an electron here, an electron here, an electron here, an electron here. That's me done 4. So I've taken away 4 and I've got 3 electrons left. Now I actually want to make my bond here. So if I put in 1 here, then I'm going to leave this one blank. Put 1 here and 1 here. And that's me done 1, 2, 3. That's me minus 3. I've done all the electrons for this fluorine, and there's 1, 2, 3, 4, 5, 6, 7. Now, the reason that I say I've been a little bit cheeky is it would be nice to continue to go clockwise. However, if I did that, it would make the diagram a little bit ugly, and I'd have to move this fluorine around and I'd have to play about with it. So I'm going to leave where I want the bond to be with that missing electron. So for the next one, I've got 1, 2, 3, 4, 5, 6, 7. And that's me done my 7 electrons for this one and my 7 electrons for this one. Now, if I draw my circles around the electron orbitals, I can see that I've got 1 bond in there, and that's me done fluorine. And this is a covalent bond once again, and I've got a nice little fluorine molecule, and that would be F2. So this is the full way of showing this. What I want to do next is actually show you valence swaps. So these have been some simple examples of some simple molecules, and what we're going to do is we're going to see a few valence swaps and play about with those, and then we'll go on to looking at some of the molecular shapes. So if we take, let's say we take hydrogen and fluorine. Now, hydrogen is in group 1 and fluorine is in group 7, so the valency for this one is 1 and 7. I can write the valency up there and the valency up there. This is going to be swaps. Now, if I want to quickly know how many atoms are going to be in my molecule, all I have to do is swap those numbers over. So I get HF, 1 and 1. Now, we don't bother writing the ones, so it just goes to HF. Now, the next one I want to show you is actually, and I'm going to do the diagram for it as well because it's a very good example and it leads us into some interesting things. So what I'm going to have is H and O. Now, hydrogen was in group 1, oxygen was in group 6. So the valency for hydrogen is 1. Group 1, and sometimes this is actually a really good technique at the beginning of the exam, is to write group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 8, and then have the valency 1, valency 2, valency 3, valency 4. Now, 4 is your maximum valency that you deal with in National 5, so we have to go down. Now, oxygen is in group 6, and you can see that in your periodic table, and that means the valency is 2. Now, to find out what this molecule looks like, we swap over these numbers. So we drag the 1 down to here, and we drag the 2 down to here. Then we get left with H2O. And we have water. Now, what I want to do is actually show you this in terms of the Lewis structure. So this is going to be the Lewis structure or Lewis diagram for water. Now, oxygen has a electron arrangement of 2, 6. Remember, for Lewis diagrams, I'm not going to do the inner electrons because it just clutters the diagram up. So I'm going to do oxygen, and I've got 6 outer electrons. So I've got 1, 2, 3, 4, 5, 6. Now, from my valence swap, I know that I've got 2 hydrogens, and I've got a spare electron here and here. So I'm going to put my hydrogens here and here. This hydrogen I'm going to do circles for. This hydrogen I'm going to do triangles for. And this will give us our molecule of water, which looks like this. Now, if I was to show you that as a simple molymod, what I would have is I would have my red oxygen here, and for the molymods they've got 2 little holes, and I can put the bonds in there and we get this. Now this is actually a representation of a water molecule, and as you'll see, it's not straight. It's actually it's got an angular or bent structure to it. So what we will do next is we will take a look at the different types of molecular shapes that we can get, and you do actually need to know and remember those molecular shapes. So we will go on and we will do our molecular shapes next. Okay, so what we're going to do is, now that we've done some Lewis diagrams, we are going to go on and see what these Lewis diagrams give us in terms of the shapes of the molecules. Now, the shape of these molecules, there's only 4 shapes you've got to remember, but in my experience, it's something that people do forget. And it is really good in terms of helping you visualize what's going on. And we will try and take our time to visualize what's happening each time we make a molecule. And you should just take that few seconds to think, what does this thing actually look like? So hydrogen as a molecule, and we'll talk about the diatomics a little bit later on, and we'll talk about naming a little bit later on as well. Once we've done this lesson, we'll do some naming, and that should help you get the naming nailed. But at the moment, we'll skip that and we'll just do how to visualize this for the time being. So hydrogen has 1 outer electron, and it will need to be bonded to another hydrogen to make our molecule, and that is our Lewis structure or Lewis diagram. The molymod for that hydrogen looks like that. Now, hydrogen fluoride, once I said, don't worry too much about the naming of molecules at the moment. I just want you to be able to start to visualize this stuff. We'll do all the naming a little bit later on. The hydrogen has that 1 electron again. However, the fluorine has 1, 2, 3, 4, 5, 6, 7 outer electrons. And we can put our orbital around there like that, and our hydrogen orbital around there like that. That is our single covalent bond. Now, that hydrogen, if we count for that hydrogen what's within its orbital, it's got 2 electrons, and so it's happy because it's got a full outer shell of 2 electrons. The fluorine, if we count what's in that fluorine's orbital, it's got 1, 2, 3, 4, 5, 6, 7, 8 electrons, so it's happy as well. And the molymod for that looks like this. And so we've got hydrogen fluoride, and our little molecule there is linear once again. Now, the interesting one here is carbon dioxide, and carbon dioxide has got 2 oxygens. Now, it can be a little bit tricky to see how we're going to build this molecule. Whenever you've got multiple multiples of one type of element and a singular other type of element, whatever is the singular, you want to make that your central atom. And so the carbon is going to be my central atom. Now carbon, if I do this up here so it's a little bit out the way, has a electron arrangement of 2, 4. For our Lewis structures, we're not going to show those inner electrons, so I just need to worry about those 4. So I'm going to put these in as circles 1, 2, 3, 4. Now, my oxygens are going to go here, and oxygen has an electron arrangement of 2, 6. Once again, not drawing the inner electrons, and I'm going to draw the outer electrons. 1, 2, 3, 4, 5, 6. And then on the other side, I am going to draw in an oxygen, and I'm going to put in, this time I'm going to use triangles just to make this separate and easy to see. 1, 2, 3, 4. Now, because this electron's the furthest away from this carbon, I want to put my 5th electron in here, and because I've got 2 electrons up here, to make the diagram easier, I'm going to put the electron down here. Now this will take practice. Carbon dioxide's probably the nastiest one that they will ask you to actually draw out, and it's nasty because it's got two sets of double bonds involved. And so when I do my orbital around this oxygen, I'm gonna have to include both this electron and this electron with these 2 electrons here. So I'm gonna do this for this oxygen, and for this oxygen I'm gonna go around those 2 there. Now the carbon has to go around this one, and this one, this one, this one, and this one. Now that is a very, very ugly diagram, and I'm honestly not sure if you'd get the mark for that. It's pretty ugly looking. However, what we can do is we can make this look a lot neater, and we can think to ourselves, right, how am I going to structure this so that it looks neat? And I'm going to hopefully show you how to do that. Now, this is me going from you guys never having seen this. So these 2 electrons here are going to be bonded, and I want to keep them on this side of the molecule. These 2 electrons here are going to be bonded as well, and I want to keep them on this side of the molecule here too. So what I want to do is I'm going to draw this again, and I'm going to start off with my carbon in the center there. Now I know I've got these 2 and these 2 like that, so what I want to do is do a triangle, a circle, a triangle, and a circle here. On this side I've got my circles and X's, and I've got 2 X's and 2 circles, so I want to go XO, XO. Now, my oxygen from this diagram has 1, 2, 3, 4 left, so I can put them in 1, 2, 3, 4, and this oxygen has got 1, 2, 3, 4, 1, 2, 3, 4. Then I can draw my carbon orbital like that, my oxygen orbital like that, and my other oxygen orbital like that. And that is carbon dioxide. That is a particularly nasty one to have to draw. What you're showing there is you've got a covalent bond there and another covalent bond there, so that's a double bond, and you've got one there, and that's another double bond. If you count the electrons around this oxygen here, you've got 1, 2, 3, 4, 5, 6, 7, 8. So it's got a full outer shell. The carbon has 1, 2, 3, 4, 5, 6, 7, 8. Full outer shell. This oxygen, 1, 2, 3, 4, 5, 6, 7, 8. And the diagram looks okay for it. That, I'd be hard pressed to say if you would get the mark for that. Technically, everything is there in terms of them being looped around by the orbitals, but it's not a particularly pretty way to put it. If you're working it out from first principle, and it's a molecule you've never seen before, that's actually a good way to do it. Then you can neaten it up and turn it into your final Lewis structure. Now that, from the perspective of our molymods, we've got 4 openings for the carbon, and we've got 2 oxygens here. So with the molymods, these bonds are actually slightly longer to allow you to show this type of bonding. So this is a double bond between the carbon and the oxygen, and what we're going to have is another double bond between the carbon and the oxygen. Like that. And that is our linear molecule, and that's what that looks like there. And that's that double bond. If we remember back to the hydrogen, those two, the sharing of 2 electrons is a single bond. The sharing of 4 electrons here is a double bond. So each pair is a single bond. Now that is your linear molecules. The next one we'll move on to is our angular molecule. Okay, now the next one that we've got to cover is a step up from the linear, and that is angular. Now, the only one that they ever really seem to talk about is water in terms of it being angular. One of the reasons for that is that figuring out why it's angular can be a little bit weird, and it's to do with lone pairs of electrons. So what I'm going to do first is I'm going to show you the Lewis structure for the water molecule, and if you stick with this method of drawing water, you'll always find that the actual Lewis diagram or Lewis structure shows you what it should be. So interestingly enough, this is actually hydrogen oxide, or sometimes called dihydrogen oxide. The oxygen is the central atom because it's the only one of that particular element, and we've got 2 hydrogen atoms of that element. So I'm going to start off with oxygen. The electron arrangement is 2, 6, so I can put in 1, 2, 3, 4, 5, and 6. Now I've got 2 atoms of hydrogen. These are my unpaired electrons, so I can put in a hydrogen here, and I can put in a hydrogen here, and the electrons for hydrogen there like that. I can put my orbital around the hydrogen, and I can put my big orbital around the oxygen, and we've got now 2 single covalent bonds that are holding this structure together, and it's angular. What you'll notice is these are called lone pairs of electrons. Now these lone pair of electrons cause a repulsive force. If we think back to our basics for charge, 2 positive charges will want to force each other apart. 2 negative charges will also want to force each other apart, and a positive charge and a negative charge will want to move together. So this is quite a bit of negative charge up here, and it actually forces our water molecule round into this angular structure. Now, the concept of lone pair electrons and additional repulsive force is not within the National 5 course, really. And so whenever they give you a question about an angular structure, it's probably going to be water, and that's the one that they're going to use as an example. Right, so the next shape that we've got, so our next molecular shape deals with another lone pair and yet more repulsive force, which once again is kind of in the course, kind of not. And so they're going to use a standard template for these ones. So this one, trigonal, pyramidal. I'll write that again so you can see it a little bit better. So trigonal, pyramidal. And this is actually going to be usually NH3. Now, when we do this, our nitrogen has 1, 2, 3, 4, 5 electrons, and our hydrogen has 1 electron. 1, 2, 3, 1 for each of our hydrogens, and we can do our orbital around there, and our orbital around there, and our orbital around there. Then we can do our big orbital around here, like that. Now, when we show this as a diagram, this is a lone pair up here, and this is a two-dimensional plane, but we're actually producing a three-dimensional object. So that creates some problems for us. So what I'm going to do is I'm going to bond our hydrogens in, and so we've got our hydrogens, and I'm going to represent the lone pair up here with this little lone pair plastic symbol here. Now, if we look at this, if we've got our hydrogens out in our plane here, our lone pair is actually in the wrong position. So we've got to show this like that. Now, this is actually a little bit tricky to do that using this type of diagram. So what I want to show you is how we can convert this diagram into a three-dimensional diagram on a two-dimensional plane. So what I'm going to do is I'm going to rotate this molecule so that this bond is flat on my hand, and that would be flat on the page. If that's like that and it's flat on the page, this hydrogen here is actually going back down out of the page, and this one's popping out towards us. What you'll also note is these are not coming flat out of the nitrogen. These are actually at an angle slightly away from that lone pair, and once again it's because those negative charges will try and repulse each other, and those bonds are actually a field of negative charge, and we've got a big negative charge up here. It's going to force our bond angle down the way. So I'm going to start with nitrogen in the middle, and the way that I'm looking at this, I've got my one bond right there on the flat. So I'm just going to have that as a flat bond, but it's slightly angled down the way. So I don't want to do it straight out. I want to do the nitrogen with this bond coming just slightly down the way. Then this hydrogen's coming out towards me, and I can show that with a triangular shape there. And I can put my hydrogens in like that. This hydrogen's going back behind, and I can show that with a dashed line. Now, that triangle there can sometimes be shown as that. So these two things mean the same thing, means it's coming out towards you, and I've got my lone pair of electrons up there, which isn't a bond, and I haven't shown them in this particular diagram. So that is trigonal pyramidal. It's one of the more complex ones. However, the good thing is that ammonia, NH3, is really the only example they're going to give you of that, usually. Once again, it's because lone pairs kind of come up in the course, kind of don't come up in the course. It's a bit of a grey area. So this one is the molecular shape for our ammonia, and we'll cover ammonia again in Unit 3, and it's a really interesting molecule, and we'll be talking a lot about it later on in the course. Right, now we've just got our last molecular shape to do, so this will be the very last one, and this will be the end of the lesson for today. I appreciate this lesson's probably a little bit longer than the half hour I promised you, but we'll get this final one done. So, and this is our fourth molecular shape, and this is a tetrahedral. So the classic one for our tetrahedral is our methane molecule, CH4. Once again, I've got a single element of carbon and a multiplicity of another element, and so this is going to be my central atom, carbon, in there. And I'm going to have 1, 2, 3, 4 outer electrons, because the electron arrangement is 2, 4. If you forget the electron arrangement, it's in the data book, and you have to be using that data book throughout the year. Now I've got 4 hydrogens, and I can place them around here like this. And each hydrogen has 1 electron. Oh, do a solid square, and I'll do an empty square. Well, that makes a vague amount of sense. I'll do the orbitals for each of my hydrogens. And I'll put that around like that. Now, once again, we have a 3-dimensional structure on a 2-dimensional plane, and we can highlight this once again. So I will have my central carbon atom, and I'll have my 4 hydrogens, round like that. Now, these are all single covalent bonds, which I can represent with my single covalent bond links. And I'll put them in the carbon first. Oh, and this is our nice little tetrahedral shape here. And that's our tetrahedral. Now, just to be clear, it looks very similar to this, but there is no atom up here in the trigonal pyramidal shape. That's a lone pair of electrons. There is no atom nucleus up here. There is just a pair of electrons. So that molecular shape looks like that when you draw it. This tetrahedral has got an atom in that position. Now, what I want to do with this one is have 2 bonds on the flat plane, and that means this one's going to pop out and that one's going to go back into the page. So if I draw that out, I've got my flat bonds there, I've got my triangle coming out there, and I've got my hydrogen going back there. So with all of those bonds put in, and the hydrogens drawn in, my molecule looks like this, and that is my tetrahedral molecule. So, takeaway from today is the valence swaps the Lewis structures or diagrams, sometimes called dot and cross diagrams. And finally, those molecular shapes. So just very quickly to go over them. Again, you've got the linear, you've got your angular, you've got your trigonal, pyramidal, and bearing in mind this one is forced down the way slightly, and finally your tetrahedral, which is the last one we covered up here, and that's them. Once again, you can make your notes out of pausing the video and taking down what's on each sheet. The next thing that we will do is we will do some tactics on how to name our molecules and ionic bonding. So next lesson, we'll cover those. Right. Enjoy the stuff that was put on Teams. It should get you pretty used to using that data book.